So it's time to get started on a new chapter, which is gases. Gases are in Chapter 5. Gases are one of the fundamental states of matter. There are some elements of the periodic table that naturally exist as gases. Almost all of the diatomics, that's hydrogen, nitrogen, oxygen, fluorine, chlorine, almost all of the diatomics, these are also diatomics, but they are not gases, are gases in their natural state. And then all of the noble gases, that's group 8A. Noble gases are not very reactive compounds. They're relatively inert. That means not reactive. They just exist as gases. What kind of properties do gases have? Well, gases take the volume and the shape of their container. If you put them in a volumetric flask, they will completely fill that volumetric flask. This is a brown gas. It's not liquid. You can't top it off at this meniscus. You can't top it off at this line, volume line, and hope that all the gas stays below that. No, it doesn't work. Gases take on the shape and the volume of their container. They're very compressible. So I could take this same amount of gas in this, let's say, 100 milliliter flask. I'm not sure if that's what size it actually is, but if it were, and I can compress it into a smaller state. When I compress it into a smaller state, it changes things about the volume it occupies, obviously. It changes things about the pressure inside that container, changes a few variables, but it doesn't change the amount of gas that I have. Okay. They mix evenly and completely when confined in the same container. What that means is if I blow out carbon dioxide, that carbon dioxide will intermingle with all of the gases in this chamber. If I were to blow carbon dioxide into this, it will mix evenly with the NO2 gas, that's probably what that is, that's already in that container. They have low densities. Yeah, sure. What kind of measurements will we make to quantify a gas? I've already mentioned a couple, but one I have not mentioned is temperature. Temperature affects the properties of a gas. Higher temperature means the gas particles will be moving more quickly. Higher temperature is needed sometimes to turn a liquid into, not sometimes, is needed, period, to turn a liquid into a gas. The higher the temperature, though, the faster those particles are moving. Steam is the gaseous state of water. Steam starts to become the standard state at 100 Celsius, but steam still exists at 300 Celsius. 300 degrees Celsius steam will burn you much worse than 100 degrees Celsius steam, but it's still steam nonetheless. Volume is the one that I've already talked about. We assume that the volume of the gas is the volume of container that's holding it. You have a 100 milliliter volumetric, you have 100 milliliters of gas. You have 10 liters flask or beaker or chamber of some sort, you have 10 liters of gas. Pressure we will talk about a bit more, but that's one of the variables. And then moles, how many molecules are in the container, because moles, how much you have relates to the properties of a different gas. Okay. So pressure, if we take you back to physics for one quick second, pressure is a measure of force over area. So in this barometer, you may have heard of a barometer before, atmospheric pressure, the gases in the atmosphere put pressure on this pool of mercury, and this pool of mercury rises up this little tube. And depending on how much that mercury rises in the tube, that tells us what the atmospheric pressure is. That tells us that tells us how much pressure the gases in the atmosphere are exerting on that barometer. If we say they exert enough pressure to raise that mercury by 76 centimeters, 76 centimeters is also known as 760, that's a 6, millimeters. We say it raised the mercury by that amount, so one of the units of pressure that we will talk about is 760 millimeters of mercury. The unit is actually millimeters of mercury, how much the mercury has been raised up that tube by the force exerted on the mercury on the outside by atmospheric pressure or some other gaseous pressure. What other units will we see? Well, Newton per meter squared, that's more of a physics-y kind of unit, but a Newton per meter squared is called a Pascal. We will talk about gas pressure in pascals a little bit, not a lot. We will talk most likely in atmospheres, atmospheres or millimeters of mercury. So 760 millimeters of mercury, that's this bit over here. 760 millimeters of mercury is defined as 1 atmosphere. So this, we say, is 1 atmosphere of pressure, just like it's 760 millimeters of mercury. 1 atmosphere is sometimes converted to pascals, but more often even than that, converted to kilopascals. So 101.325 kilopascals is 1 atmosphere. All right. So manometers, a barometer is the thing used to measure atmospheric pressure. A manometer is one of these. These are an arm that has some sort of gas in it. That gas exerts pressure on this tube filled with mercury, and depending on how much it raises the mercury, how much it displaces the mercury, we can know the pressure of the gas inside this manometer. If you have a manometer that is under vacuum, so a closed tube manometer of closed end, the pressure of the gas is the height that the mercury was displaced. So this one is very simple. The pressure of this gas is 400 millimeters of mercury. And if you needed to convert it to atmospheres, 1 atmosphere is 760 millimeters of mercury. That's a G too early. Whoops. I didn't do that conversion. I'm not going to do that math for you, but if you needed to do so, that's that. This other one on the right is the same kind of deal, except up here, that tube is not under vacuum. It is open to the atmosphere. So what that means is the atmospheric pressure is pushing on that mercury. If you could see my hands, atmospheric pressure is pushing on that mercury, and the gas is pushing on that mercury. Both gases are pushing on the mercury in a tug of war. And so because the gas seems to have pushed the mercury down more than the atmospheric pressure has pushed the mercury down, it lets me know that the pressure of the gas is higher than the pressure of the atmosphere. If atmospheric pressure was higher, we would see a manometer. Oh boy, this is going to be a great little drawing right here. Have a gas that has a lower pressure than the atmosphere. You're going to see some sort of picture like this, where the gas did not push as hard as the atmosphere did because the pressure of the gas is lower. So you can find the pressure of the gas for an open-end manometer through this kind of equation. So you have to know atmospheric pressure plus the height that was displaced to tell you the pressure of the gas. If you were to see it this way, you're going to subtract H because your H is still telling you the height difference between these two. And so your gas pressure has to be lower than your atmospheric pressure. So you're putting in a negative H in that sort of value. Okay. Illustrated below is a manometer. Above the mercury column is vacuum. If the difference in the heights of the mercury column is this, what's the pressure of the gas in atmospheres? All that is a simple conversion. Because we know that it's an open end, it's a closed end manometer. So it's just converting millimeters mercury to atmospheres. And that's dividing by 760. And if I look at my little cheat sheet that I've already done the math, I got 0.484 atmospheres. Not bad at all. What about in an opened end manometer? The height is 309.55. Barometric pressure is 744.4 millimeters of mercury. All I did was change that centimeters into millimeters because that's what I'm more used to. What's the pressure of the gas? Atmospheric pressure plus H, because I know that my gas has displaced more mercury than my atmosphere has. So my pressure of my gas is 1,053.9 millimeters of mercury. And it doesn't say in atmospheres this time, but I'm going to go ahead and write it down so that you can double check your math. 1387, if I did my math right, atmospheres. Yeah. This little video link at the bottom, I'm not going to go ahead and click now. I thought about it, wanted to plan on it, but no, we're going to keep moving forward. But it tells you how does pressure and temperature and volume and all those variables, moles, relate. We're going to dive on into the details and say Boyle is a chemist from long ago, like 1600s, and he discovered in the 1600s that there's a relationship between pressure and volume. He said pressure is proportional to 1 over volume, meaning they have an inverse relationship. As pressure increases, volume decreases, and vice versa. So he wrote it down this way, where he said the pressure multiplied by the volume is always equal to some constant number. And we're going to call that KB because we're going to say that's Boyle's constant. Pressure times volume is equal to some constant, always. Okay. Charles also studied gases some 100 and something years later, and he said, let me study volume and temperature. Boyle has already said there's a relationship between pressure and temperature, but let me study volume and temperature. And he studied volume and temperature and said, these seem to be directly related. Volume goes up, temperature goes up, or as temperature goes up, volume goes up, vice versa as well. So he said, let me say volume over temperature is equal to some constant. We're going to call it Kc because it's Charles' constant related to, Okay. Avogadro, he said, I want in on this. I want to know how moles and volume of gases relate. And he found that moles is proportional to volume directly as well. Increase moles, increase the volume, decrease moles, decrease the volume. Directly related. So he said, must mean volume over moles is equal to Avogadro's constant. So Boyle studied pressure and volume, Charles, volume and temperature, and Avogadro, moles and volume. And then someone came along and says, you say this is equal to some constant, and that is equal to some constant, and that is equal to some constant. What if I combined all these constants to say some constant must be equal to pressure times volume divided by moles times temperature? If I know that each of these individually equals some sort of constant, there has to be some sort of constant relationship between all of those variables as well, and this is what we came up with. So this R is called the ideal gas constant, or just the gas constant, and we will see that one a lot. On the next slide, we're going to talk about it a little bit more, but before I deviate from here, Boyle's law, it's true that P times V equals some constant, but more often you will see Boyle's law represented this way. P1, V1, P2, V2. You ever seen an equation kind of like that? Last week. So P1, V1, P2, V2, what that means is if I have a system at some pressure and volume and I change the pressure, the volume will change by the same proportion. If I have a system at some pressure and volume and I change the volume, the pressure will change by the same proportion. Yep, equal and opposite. It's true. We can do the exact same thing with Charles's law to say V1 over T1 equals V2 over T2. If I have some sort of system, volume, and temperature, and I change the temperature, the volume changes automatically. Or the opposite, if I have some sort of volume and temperature system and I change the volume, the temperature will change automatically. And the last one, we don't really see a lot of proportions in the moles, but we could write one, V1 over N1 equals V2 over N2, but that's not usually the case because you have to be able to add in more moles to do that. So moles is not usually in a proportionality constant, in a proportionality equation, ratio equation, like Boyle's and Charles. So don't do Avogadro's that way. Okay. So we said, if we combine all those laws, we get this equation up top, that some constant is equal to P times V over N times T. Well, if we have the system described here, that is 273 Kelvin, that's our unit of temperature in all this gas stuff. We'll see it in temperature in Celsius a lot, but Celsius plus 273 gives us Kelvin because our standard unit of temperature is Kelvin. 273 Kelvin and 10 liters, and I have some gas in there. And I put enough gas so that eventually the pressure of the gas is equal to 1 atmosphere. So I put enough gas into here to fill this 10-liter volume and give it a total pressure of 1 atmosphere. If you do that, how many moles did it take to fill this chamber to 1 atmosphere? Apparently it took 0.446 moles. So if I knew that it took that many moles to get to this pressure, I can solve for what my constant must be. So plug in all those numbers and we get 0.0821 liters times atmospheres per mole Kelvin. I know I said that backwards from how it's written, but it's how I always say it. 0.0821 liter atmosphere per mole Kelvin. It's a long set of units and they cannot be simplified. That is my ideal gas constant, this guy. You'll see it written this way with those -1 exponents often. Instead of writing the equation like this way most of the time, we write it PV equals nRT, where R is my ideal gas constant. PV equals nRT. Ideal gas law. Yep, isn't it lovely? All right, wrapping up this gas mess. When we see gases, there are 2 major types of problems we will have. One problem is we have one unknown variable. There's no change that's happened, just one unknown variable. Given this, find that. And given this, find that. Let's use the ideal gas equation. A sample of nitrogen gas is kept in the container of 2.3 liters, temperature of 32 Celsius, pressure of 4.7 atmospheres. Calculate the number of moles of gas present. I won't do the whole math, but it would be 4.7 atmospheres times 2.3 liters. PV equals N, we don't know, 0.0821 because it's a constant, liter atmosphere per mole Kelvin, times 32 plus 273, I didn't pull out my calculator whatsoever, solve for moles if you have one unknown quantity. The other type of problem is make a change and see what happens. You're going to use one of the ratio equations for that. So Charles and Boyle's law have been combined in this ratio set up here. It's totally fine to use one or the other. Yeah. 46 degrees, a sample of this, a sample of ammonia exerts the pressure of this. What's the pressure when the volume is reduced to 1/10 of the original value? So plug in all your known values. 5.3 atmospheres times some unknown volume. We're going to say it's 1 because our next volume is 10%, 1/10 of the original value. What's the pressure? And we know that it's at 46. The truth is the temperature doesn't change. So we could shortcut and leave the temperature completely out of that equation and use it as a Charles equation instead. Nope, a Boyle's equation instead. But you can put it in there. It's just dividing by the same number on each side and solve for P. Okay. All of that previous stuff was kind of assuming that you have one gas in the chamber. You can kind of do some of that with multiple gases, but let me give you a couple of tools to deal with multiple gases first. So if you have more than one gas, you need to take advantage of something called Dalton's law of partial pressures. Dalton's law of partial pressure says pressure is additive. So if I have a chamber that has some gas in it, so it's exerting a given pressure, and I have another chamber that's the exact same size, if it's in a chamber on its own, it exerts a given pressure. If I combine those two gases in the same chamber, I'm going to get something called P total, which is the sum of the pressures of each of those gases if they had been alone. So this P1 is called the partial pressure of gas 1. Oh, that's great spelling. P-R-E-S-S-U-R-E. Oh, that's totally illegible. Made it worse. P2 is called the partial pressure of P2. So it's the total pressure in the chamber is combined is comprised of the partial pressure of P1 plus the partial pressure of P2 to get me P total. So there's one other thing that we need to consider when talking about these. If I have a chamber that has multiple gases in it like this, I can find out the partial pressure of one of the components if I know the number of moles of that component. Yeah? I can find out the partial pressure of another component if I know the moles of that component. R is a constant. It's not going to change. If they're in the same chamber, the temperature and the volume are both going to be the same as well. So all that relates here is the moles of my gas, my moles of A, and my partial pressure of A. The only variable responsible for the pressure being different for the different gases is the number of moles. So P total is the sum of the partial pressures. Yep, we've already said that. This is something new. This says the mole fraction, it's a Greek letter chi. It's not just a regular old X, it's a Greek letter chi. The mole fraction is the part over whole. And mole fraction should always be a number less than 1. So how many moles of A divided by total moles of gas, period. And the mole fraction of B will be the how many moles of B over the moles total. So the mole fraction times the total pressure. Mole fraction of A times the total pressure tells me the partial pressure of A. The mole fraction of B times the total pressure tells me the partial pressure of B. So the summary down here is mole fraction times P total is equal to the mole fraction times P total is equal to the partial pressure of whatever that is you're giving the mole fraction of. And we'll stick that in there. Mole fraction is part over whole. Part over whole. All right, that's enough gases for today. Goodbye.